Hello, my name is Taylor Marion, and I'm here to present my report on finite state machine-based vulnerability detection in binary executables. The motivation behind this research project is that I've worked in various roles between military cyber operations, government contracting, and private sector work, where I've worked in development as a reverse engineer, and as a source code reviewer and various other tasks where I've had to perform some sort of vulnerability detection. Sometimes I have source code, sometimes I did not. And so this really hit home to me because I know firsthand that this can be a very frustrating and time-intensive endeavor. And a lot of these traditional methods for like source code review and things of that nature require source code. And that just isn't always the case. You don't always have access to source code. There are a number of existing tools and methods tackling the same problem of vulnerability detection. But a lot of the existing tools have their own unique little troubles. With dynamic analysis and fuzzing, these methods are very lengthy, they're computationally expensive, and they're imprecise. For fuzzing especially, by its very nature, it's imprecise. You're essentially just throwing random garbage data at a process and hoping for a crash. And every new test you launch is a new process being ran. So it's computationally expensive, and even for fairly simple tests, they can take hours, and in often cases it's one of those tasks that you let it run overnight, come back in the morning, and hope you have something worth investigating. Dynamic analysis, it's very much the same. Each time it runs, it's a new process, and you run into issues of path explosion for more complicated endeavors. Manual reverse engineering is always an option, but it's also extremely time consuming, and it requires deep expertise. I've worked as a reverse engineer as a government contractor, and I would not call myself an expert reverse engineer by any means, but I've worked on a number of security teams, a number of different offices, and I understand that skill set, even at a basic level, is not a common skill in a lot of security teams. So for these reasons, compiled binaries remain a critical blind spot for vulnerability researchers. That's where finite state machines come to play. Finite state machines offer a static, structured, and interpretable tracking of variable state transitions while keeping computational expense low. When I was thinking of this project as my research question, it seemed very almost poetic that finite state machines and lexical analysis and parsing are used so heavily in compiling software from source code to compiled binary code that it seemed just almost just poetic to use them to go the opposite direction of converting compiled code into detecting vulnerabilities in that compiled code. So the core research question here is, can finite state machines detect vulnerabilities directly from disassembled binaries without having any access to source code? There's no source code, no contextual hints or clues. It's just as a pure black box test, can it find these vulnerabilities? And that's what we're trying to answer with this report. So before we go into the details of the project, I'm going to address some high-level goals of the project. Firstly, this is just to assess validity. I am not aiming to produce a production-ready deployment system. This is just an investigation for initial feasibility. With feasibility in mind, it was really important to me that we designed a tool that can be run on a standalone computer. A lot of security teams don't have access to high-powered computing clusters. A lot of individual researchers, which do a lot of really important work, are spending big bucks of their personal money on their own, virtual cloud servers and systems. And it was really important to me that we develop something that can be run on a small standalone system. No supercomputers, no giant high-powered computing clusters, no GPUs that cost thousands of dollars, just something that can be run on a decent laptop from an individual researcher. Because this is a initial feasibility investigation, I wanted to control the scope. So just take it one vulnerability at a time to address if this approach is valid and warrants future research in the future. So with that in mind, I chose the vulnerability CWE, Common Weakness Enumeration 457, which is the use of uninitialized variables. I chose this vulnerability in specific because I've worked with it before throughout manual analysis, and it should be a fairly simple vulnerability to detect and map and model into a finite state machine. Essentially, you're looking for a variable that has been read before it has been written to. So it's, from a finite state machine perspective, it's simple. There aren't that many states. There's very few transitions. So it should be an easy model to assess validity of this approach. So before we can analyze any compiled binary, we need to have the compiled binaries to test. And during my initial research, I came across the Juliet Test Suite. This is a giant test suite of thousands of software samples, all built in C, across numerous vulnerability classes. This was originally produced and created by the NSA and is now publicly available through the NIST, the National Institute of Standards and Technology, website. I initially had some trouble compiling this in an automated fashion, but I found a GitHub repository by Alexander Richardson, which extended the use case, which extended the usability of the test suite and made it a lot more automation friendly. So using that GitHub repository, I was able to compile the C source code in an automated fashion into ELF binaries. From there, I used object dump to disassemble those binaries into x86 64-bit assembly instructions. And this is where the project really starts to take off, because if you have a compiled binary that you'd have zero context, zero source code, zero hints about what's going on, this is your starting point. So once we have the disassembled binaries, the program, the test ticks over. That's where we perform tokenization and normalization. We reduce the assembly instructions into abstract memory operations, mainly read, write, and end. And for the simple case here that we have, that's really all we have defined. Any other operations are not going to have an impact on a use or a uninitialized variable. So any other operations that are not read, write, or end get classified as a no-op or no operation. That is a very simplified tokenization language. Some might even say oversimplified, and I would be inclined to agree with that assessment. But for the purposes of initial exploration into this approach, simple is better. We can make it more complicated later on for future research. And one of the benefits of this tool is that we don't need any other intermediate data set. We can work directly with the the disassembled assembly instructions. The design of the finite state machine is pretty simple. We only have a handful of states and a couple of transitions to worry about, which made this a really good model for initial feasibility. So the core states we have here, we have allocated, which is whether that's on the stack or the heap, the system is reserving space for that data. Something has been initialized, that means the variable has been written to. Some languages and some functions, like calloc, when you reserve memory using calloc, it automatically initializes that data as zeroed out. That would be initialized, but using malloc, for example, does not initialize data, which is where these vulnerabilities come into play. So if you're to, and then we have the core state of read before init, which is before it's been initialized. So if you declare a variable and you read to it first, that's really the heart of this vulnerability class. Our key transitions that we have to worry about here are read and write. Any other operation really doesn't affect the vulnerability class at play here, so it's considered a no-op. Beyond that, all we have to worry about is the end, whether that be the end of a function or the end of the program as a whole, in which case terminates and whatever class we're in, whether it's vulnerable or safe, is the answer there. So evaluating the finite state machines on the Juliet Test Suite, we have a total of 926 safe functions and 926 vulnerable samples to test with. We're going to define some values. These should be familiar to anyone who's ever done any kind of statistical analysis or large-scale testing, but it's really important that we define these terms here. For true positives, these are vulnerable functions that are correctly detected as vulnerable. False positives are safe functions incorrectly flagged as vulnerable. We have true negatives, which are safe functions correctly identified as safe. And we have false negatives, which are vulnerable functions that are missed. So overall here, we see our results. Not extremely impressive, but there's a couple of details that I really want to point out here. Number one is that we have a pretty decently high precision of 79.35%, so just under 80% precision. That means that when we classify something as vulnerable, it usually is. We're usually right. Now, however, recall is pretty low. It's under 47%, so which is not great. That's pretty bad, to be honest. That means that our model misses some vulnerabilities. So we have a pretty high number of false negatives, which brings our general accuracy and recall quite low. However, we are pretty good at spotting safe files when they are truly safe. Now, 811 out of a total 926 samples were correctly identified as safe. So we're good at finding safe functions, and when we do say something is vulnerable, we're usually right. So overall performance is not great, but there's a lot more in the details here, more than just the surface level scores. So as you can see, we do have some strengths and weaknesses in this approach. The strength is that we have high precision. When we flag a vulnerability, it's usually correct. It's lightweight and deterministic. There's no need for heavy compute or probabilistic models. It gives you a yes or no answer, and it's not always right, but that can be improved later. The key thing is that it's lightweight and it's efficient. This was entirely built on a laptop. It was run on a laptop, and even going over 1,852 samples, it was blazing fast. And it's easy to interpret and debug. These states and transitions are very easy to model, very easy to visualize. It would not be very complicated to build a visualization module after this to clearly locate exactly when something turns vulnerable in a step-by-step way. There are some weaknesses. We have low recall. So as of right now, many vulnerable samples are being missed. And because our tokenization and normalization is so simplified, we do have limited expressiveness. That means that with more complex or indirect patterns, things that have, say, for example, nested function calls, those are an area where I would need to do follow-on research to determine if that's being correctly passed. So if a vulnerable function is detected 4 nested calls deep, is that being properly relayed back to the original calling function? And it is sensitive normalization and token abstraction, because like I said, the tokenization is just so simple for this initial research that it might be doing a disservice. It might be misclassifying a lot of these samples. So while these show promise for interpretable lightweight analysis, they need to either be greatly improved with a lot more complex logic or paired with other systems as part of a pipeline. So if this was part of a pipeline of other tools, this would just be one more piece of information to weigh the ultimate decision on, not a standalone tool. So we do have some limitations in future work. So right now we're restricted to a single vulnerability class. That was by design, but it is still a weakness. It's a limitation. The token normalization simplifies real-world logic immensely. Real samples are probably going to be much more complicated because the models that we trained on are small, clean, they don't have optimization or obfuscation, they're not packed. They're very clean, sanitary test cases. So for future work, we would expand to multiple vulnerability categories for broader generalization. We would incorporate richer disassembly features that would include register use and control flow. So in assembly, quite often, different registers could have different impacts on the vulnerability. So using the register RAX versus RBX could impact how a vulnerability is classified in some cases, which would just be that more complex tokenization I mentioned. And ultimately, we would want to test on obfuscated or optimized samples. We'd also want to test on samples that have been packed and even look at binaries that were compiled with a different compiler. GCC is not the only compiler out there, so we'd want to see if these same patterns emerge in other compiler binaries. So in conclusion, I believe that this project has demonstrated feasibility of this method of using finite state machines for vulnerability detection. We have high precision, which shows potential for targeted static analysis. Yet, our current recall and overall performance just indicate further refinement is needed, definitely. The key insight I want to drive home before I conclude is that we've provided a foundation for future research. This was never intended to be a standalone tool. This is just step one in a future stream of research. Whether this be a standalone tool or that's built upon in the future, or it's just one part of a pipeline involving dynamic analysis and machine learning-based methods, that remains to be seen. But we have a foundation for future research, which is a success in my book. With that, I will conclude my report. I thank you all for your time and have a wonderful break.